Okay, so we just heard from Jose about all the neat things that the atmosphere does with tilting the wavefront and the phases and turbulence. Now we're going to see the very boring, simple things the atmosphere does. This was a problem that was still dealing with it, and especially as we go to higher resolution. And that's just your plain vanilla atmospheric refraction. And so atmospheric refraction, Jose mentioned it, but it's very simple. If we look at it on a large scale, we have the spherical shell of atmosphere around the Earth, and with some refractivity, index of refraction. And so as the light ray goes through, it's just like a big lens, and it just spherical lens, and it bends that light ray as it goes through. And so that means when you look out at some source out in the sky, you see it bent, the ray coming in is bent, and so you see it apparently at a different position than where it really is in the sky. And so this can be treated, the simplest approximation is just to treat the atmosphere as just a simple plane parallel horizontal atmosphere, and you can use the simple Snell's law, and you can get this very simple approximation up here just using the tangent of the zenith angle. So that's the angle away from the zenith of your object that you're looking at. And you care about this index of refraction of the atmosphere at mu naught there. And you calculate simply the tangent, and you can calculate the refraction. And this is actually accurate up to a zenith angle of 68 degrees. So well away from the zenith, this very simple approximation is good enough. Back in 1787, this was solved, got even more, was treated even better, and you can break this out into a series of tangent of odd powers, and there's the, you still have the R, the refractivity, the index of refraction -1, and the zenith angle. And all he had to introduce was this equivalent atmospheric height, this beta, or the H0. And that gives us a ratio between this H0 and the R0. The R0 is the diameter of the Earth. H0 is just this equivalent atmospheric height. So how much of a equi-dense atmosphere would you need above the observer in order to have the same pressure at their height? So with this simple approximation, slightly more complicated, but still very simple, he was able to get an approximation that was completely independent of the atmosphere and the density and all how it changes with height. And now it's accurate up to a zenith angle of 74 degrees. And so this is good. As you start, really, as you can see, this is really a long integration problem. You need to integrate this ray through the whole atmosphere, and you need to take into account the changes in the density and the temperature and so on along the propagation of that ray. Luckily, though, a simple approximation like this, or there's others, get you up to a large zenith angles, which are mostly good enough for solar observations. There are effects at the horizon, though, when you start looking very low in the atmosphere. Actually, what you can get is the horizon is depressed. Actually, the sun rises. We see the sun even while it's still below the horizon because of the refraction. The light ray is bent near the horizon. So this is the apparent altitude down here in arc minutes. So this is only a few degrees above the horizon. And you see the refraction now is about 40 arc minutes, so greater than the diameter of the sun. And so that's why we see the sun actually a few minutes before it comes above the true horizon. What's interesting is that this varies by about 10 arc minutes just over the diameter of the sun. So what that means is that the lower part of the sun is bent up by a greater degree than the top of the sun. And so if we see the sun at sunset, we get this squashed sun effect here, where you see the sun being flattened. And if we put an actual circle around it, you see how much the sun is squashed by the refraction. So that's an effect as we get very low to the horizon. And you see that will cause the scale of the sun is now being squashed. That whole image is changing in its scale along that vertical direction. Even at a few degrees above the horizon, the shape of the sun is being squashed still by 10%. One question was, as we look at higher resolution, is this an issue even at larger elevations? Now I've plotted it over from 7 to 30 degrees, and we see how much this image scale compression is over that range where the sun is low in the sky, but well above the horizon. And you see it's 0.994, 0.996 here at 10 to 15 degrees and slowly levels off. So a few parts per thousand, which isn't bad, you would think, but we have a 4,000 pixel detector, and a few parts per thousand on a 4,000 pixel detector is still 10 pixels or more. So it's a small effect and probably won't affect interpreting the observations too much, but it would be interesting to see if we can see this compression of the images with these 4K detectors and looking and see the image scale effects. So I said 15 degrees was a typical height where we might want to start observing the sun. So now I've plotted for DKIST. This is the elevation of the sun above the horizon, plotted as a minutes after sunrise, after the true sunrise, the sun at 0 degree elevation. They all start here at 0, of course, and you see this broad spread different times during the year. The sun in the winter stays fairly low, only gets about 45 degrees up, sets after about 600 minutes. Later in the summer, it actually gets up to about 90 degrees. It will go through the zenith because we are slightly below the tropics there. And then the sun will stay up about 800 minutes. What you see here is about 1 hour after sunrise, when we can typically start observing. The sun is at 15 degrees elevation. 2 hours, we're just at about 25 degrees elevation. So the sun is very low. So one way people avoid all worrying about atmospheric refraction and these effects is they observe when their objects in the sky are higher, right? Nighttime astronomers are always looking to observe through as little air mass as possible. As Jose mentioned, that's not really the case with solar observations. We often want to observe when the sun is as low as possible, not as low as possible, but is in this sort of sweet spot where it's risen up above some of the atmosphere. We're 10 or 15 degrees above the horizon, but we don't have all the heating from the sun of the ground and of the atmosphere itself. And so this is the typical trend we see where the best seeing the seeing is sort of poor in the morning. Jose showed that one example. This is a whole statistical compilation from the site survey. And you see how the seeing, this is a probability of having this R0 above certain values, so the probability of good seeing. And you see how it sort of slowly rises up and it peaks up in here in this area and then degrades. And then we have this bad time here and around local noon, and then maybe it gets better sometimes in the afternoon. And so the typical elevations we have here when we're in this sort of spot, this is plotted in an hour angle, but I've translated into typical elevations here. So 15 degrees, that was about an hour after sunrise, and then 28 degrees up to 40 degrees where we have these good conditions. So we're trying to observe the sun when it's very low in the sky. So we're sort of we can't really wait for the sun to be as high as possible, avoid all these effects. So we're sort of constrained by that. And so what is that? The refraction is a problem, but the bigger problem is the wavelength dependence of the index of refraction. This was mentioned before, talking about AO and how this can cause effects in the adaptive optics performance. And the basic problem is that the index of refraction, which we saw before, or the refractivity, that R, index of refraction -1, is actually wavelength dependent. So that simple tangent formula has this wavelength dependence. The wavelength dependence of the refractivity of the air has, was calculated and can be approximated pretty well by a formula like this for standard temperature and pressure and so on. And if we look plot this out, you see it's a function of wavelength here. And you see that it drops sharply here. This is 4,000 angstroms here, the calcium H and K lines. And then it tapers off here and gets pretty smooth out into the longer wavelength, which is nice. But a lot of our observations here from 1,000 nanometers down to 400, there's a strong variation in the index of refraction. So what does that do? Well, the refraction, the amount of refraction in arc seconds here, you see it plotted again as a function of elevation. It goes up, and now I've plotted in two different wavelengths, and you can see that they're a tiny bit different. You see the red and the blue line. This is so I've plotted generally here two wavelengths, 400 nanometers, which is near the calcium H and K line, sort of the blue end where we get the highest resolution, and some interesting spectral lines, lots of lines in the UV, as Phil was saying, that we want to look at, and then going all the way out to the calcium 8542 line. So this is sort of the range you might expect to cover with some observations. And so if I take the difference of those two curves, right, I can calculate my dispersion. That delta R it just depends on the difference of the index of refraction, or the refractivity, at those two different wavelengths. And you see it starts down here when we're at 15 degrees. It's about 4 arc seconds, and tapers off to 0 as we get up, as it goes through the zenith. But 4 arc seconds, when we're looking at structures on the sun that are sub-arc second, or even a tenth of an arc second, is of course pretty significant, and something we're going to have to worry about. So a quick interlude here. So we learned about what the dispersion is. So there's 3 pictures here. How many of those pictures, show of hands, indicate effects due to the atmospheric dispersion? Let's hold up some fingers. 1, 2, or 3. Okay. 1, 2s. Good guess. So of course this is just a rainbow. That's dispersion, but it's not in the atmosphere. It's in the water droplets, so that's not it. This is a lunar eclipse, and it's red, not because the refraction would be less for the red rays going through the sun. And so it's not that it's more red light is being refracted onto the moon, it's that the blue light's being absorbed. They're both being refracted, the blue light more, but it's being absorbed, and so more red light gets to the moon during the eclipse. And this one is dispersion. So this is the green flash, where we're seeing the sun setting, and the only part of the sun left above the horizon is this, the green part of the sun. And it's green. The blue, again, is mostly scattered away. So to show that, so this is sort of a very exaggerated scale of what that dispersion is doing. It's basically, at each different wavelength, the image appears at a different part in the sky. And so when the sun's setting, the red sun goes down first, and then you have the green sun, which hasn't quite set yet, and you still can occasionally see that green flash, the rim of the green sun, a few arc seconds later as it's setting. And then, as I said, the blue sun is usually scattered away because of the Rayleigh scattering is much stronger in the blue, so green is sort of the spot where there's enough separation in the dispersion, but not enough scattering. So one thing you could think is, if you took a picture of the sun like this, and this dispersion was, hugely exaggerated like this, and you just took a picture, you would see the sun sort of smeared out in wavelength, right? If you didn't, if you were just taking a black and white picture, or you're taking a picture of it, you would see this spreading out of the sun. This is obviously very exaggerated, but this is actually a problem as we go to higher resolution, and we have filters which are admitting multiple wavelengths through our filter passband. We actually get smearing within the filter passband that's important to consider. So this is this airy disk, like Jose was showing before, the point spread function that you would expect from a perfect optical system. And now if I put just a narrow 5 angstrom filter and I observe through that, I'm observing different images through that filter at different wavelengths, and they're being slightly spread out. And now you see the point spread function is stretched a little bit in that dispersion direction, and here it's getting quite extreme, and this is with a 10 angstrom filter. And this is because we're looking on scales of a tenth of an arc second with at 400 nanometers with DKIST. Old slide says ATST, historical historical slide there. And so this is the Strel ratio, and this is for, when the sun's at 15 degrees. And so this is this guided, this is an important consideration. We can calculate this out for different wavelengths, and it's much more important in the blue, and so we have to make sure we have narrow filters in the blue wavelength, even when we're looking at continuum and so on. What? So these are contours of the acceptable passband in nanometers. So this would be 10 nanometers, 100 angstroms. This would be 10 angstroms. So yeah, normally the G-band, in the past we've used about a 10 angstrom filter to measure the G-band because that's sort of the width of the molecular band there. Now with DKIST we have to, the passband's about 5 angstroms, so we don't get that as much smearing in the passband. So that's all set. You don't have to worry about that so much. But just to plot again here on a blown up scale, I showed it before, but again here's the dispersion as a function of time. So at sunrise here at 0 degrees, I didn't even calculate it because there's no good formula, but as we go higher we see that dispersion changing. So this is during one day, and now I can stack these up and make a plot showing the magnitude of the dispersion as a function of time again, and then for all the days in the year. And this will change slightly. So this is actually when the sun is already 10 degrees above the horizon is when the image starts here, and then you see the contours when the dispersion between 400 and 850 nanometers is 5 arc seconds, 3 arc seconds. Around local noon here, it always gets down pretty small. That's good. But you see how there's some variation during the year in how fast it changes. In the winter months, it never gets below 1 arc second here anytime during the day because the sun is going fairly low across the sky. So this is the sort of magnitude of this dispersion, and so what that means is the images you'll see from the telescope from the different instruments are all going to be shifted with respect to one another by this dispersion effect. So you'll be measuring with 2 instruments, and you may align those optically internally, right? We'll have targets and bore sights, and we'll be able to say those 2 instruments internally we can align them. But externally there's this other effect that we can't measure through any optical means that'll cause this shift, time variant shift between these images. And so one issue is how do we line these things up? Because then of course they may be observing different structures. There's a wavelength dependence of how things look like on the sun. And so we did a test where we took a series of observations from the Dunn Solar Telescope starting early in the morning. When the elevation was started at about 17 degrees, I think, 15 to 17 degrees. And we measured that offset between 2 images at 2 different wavelengths as a function of time. And those offsets are the crosses here. And so the seeing got bad towards the end of the period, and so a lot of jumping around. But during most of the time, we get this nice curve. And then I plotted on top that red and blue curve are the theoretical atmospheric dispersion measured from that simple formula and calculating the refractivity of the air. And you see they fall along each other quite nicely. I can plot the residuals between the measured and the theoretical curve. And you see most of the time we're down just with that simple calculation of the dispersion, 0.05 arc seconds, which is still, pixel scales at the DKIST may be on that order or even smaller for things like the VBI. The pixels are less than 0.02 arc seconds. So still want to refine this. Maybe our model is a little off. But so we're able to, though, get a very good calculation just theoretically of what the dispersion is. And you'll be able to apply that to your different data from different instruments in order to align them. These kind of offsets won't be automatically calculated or applied to the data. This is something that the users will have to apply. will provide tools for doing those calculations that we have. So this is nice. It's nice we can calculate those offsets. One question is, how much do they depend when we're calculating these offsets? So the refractivity depends primarily on four things: the temperature and the pressure. And this is a plot of how the refractivity, the ratio changes if I change my temperature. And really the biggest one it's dependent on is the local temperature. The local pressure changes by so little that it doesn't really have a big effect. So we'll be able to calculate and provide corrections for that, the dispersion offsets for the DKIS data fairly accurately, I think. One other issue, though, is that dispersion is always on a fixed direction with respect to the horizon. The dispersion is always occurring perpendicular to the horizon. It's in that one direction, right? And so wherever the object is, the dispersion is occurring on this great circle between the zenith and the horizon. The issue is, though, we're looking at the sun, a celestial object. We're looking, we like to, look at the sun with solar north, or that's how we follow features. And so that angle depends on this curve, the green curve, which goes to the north celestial pole and the south celestial pole, and it creates this angle that varies during the day between the dispersion direction in black here and this celestial direction, and that's called the parallactic angle, nu, in there. And this will vary during the day. Here's a plot trying to show that. So this is in the east in the morning, this looking south, and then looking west. And so in this, here's your parallactic angle in blue, and you see it's that dispersion direction perpendicular to the horizon is tilted to one side of the celestial pole. When it's at local noon, they line up, but then later on in the day, they're tilted off in the other direction. And then with respect to solar north, it's also asymmetric, solar north being the orange line, which is what we often observe or line up our objects in. So there's an additional offset there that will vary during the year. So the parallactic angle varies during the day. That angle of the sun changes during the year. And so here's how the parallactic angle, this angle will change during the day. And so some parts of the year it's fairly constant. During most of the day here it runs up, stays fairly constant, changes quickly at local noon. Other times it's changing all throughout the day in a fairly continuous manner. And so there's different behaviors, and we'll see why that's important here in just a second. So what this means is that total dispersion that we calculated before is actually decomposed in our image into two different directions. It'll move the image in east-west and north-south, and it'll vary during the day how much is going into each of those two directions. And so this is sort of a plot of the dispersion shifted east-west and north-south during the day, and you see it's shifted and then changes direction and goes into the y direction primarily later on. So using those same data I showed before, I decomposed, we have the shifts were actually measured in our pixel plane, east, west, north, south, and we can plot them here in a similar way. Again, this is on a smaller time range. So just, as I said, starting at about 15 degrees. And now I plot that and my theoretical, and again, they're both matching up. So we're able to calculate the XY and or the east-west and north-south components and apply those to the data pretty accurately. So this is great. Like if we have like VBI images, we have big 40 arc second, 60 arc second field of views. We can shift it by 2 arc seconds or VTF. We have these big images, and 1 to 2 arc seconds. We can move these things around, no problem. We have some instruments though that are only sampling a small part of the field of the field at a time. We have DL-NIRSP, which at its highest resolution just has a little few arc second box that it's sampling. And so these shifts now are getting to be about the size of this of the field of view. And we also have the VISP, which has a slit. And that will also cause problems because then the slit is very narrow in one direction. And so this is an image showing an observation, say, of a pore. And I plotted the DL-NIRSP fields of view at 3 different wavelengths, 630 nanometers here in the blue, 850 in the green, and 1 micron, I believe, in the red. And so now you see this dispersion has caused these 3 different fields of view to be slightly shifted with respect to each other. So now the overlap between all 3 of my fields of view has now gotten much smaller. So this is something, especially when you're designing your program and you're thinking, well, I need, this many arc seconds of overlap for, 1 or 2 hours in the best seeing, you may have to, think about taking multiple tiles to sample that up, or figuring a way to deal with this, or looking at the best times of the year to do this certain observations. So this is at one time step, 24 minutes after the, I think after sunrise, or after the sun's above 10 degrees. Anyway, the elevation is at 15 degrees, and this was on the 21st of June. And I've plotted 2 arrows here. This is solar north in the red, and then there's the parallactic direction, or the direction to the horizon. So this is the parallactic angle here, and that blue line gives the direction to the horizon, and the length of that arrow changes as the dispersion changes. So this is one time step, but as we saw, the dispersion changes, right, over time. It varies in magnitude, and the direction this is going to change. So you see there's some offset between these because of this vector is not perfectly horizontal here, right? So there's a little bit of offset there. So this is a very complicated question. At a different time, and I'm going to show you a movie now, which one of these is going to move the most? The one at the shorter wavelength or the longer wavelength?
Blue one?
The blue one, because at the shorter wavelength, the index of refraction is higher. Except our telescope is pointing at the bluer wavelength. The adaptive optics is locked on this feature here, this pore, and it's tracking at 500 nanometers. So it's following the 500 nanometer sun, and the other things are drifting with respect to that 500 nanometer sun. So the one that's shifted the most is actually the one in the longer wavelengths. So, and then as the refraction decreases as we move on during the day, they line up on that sunspot, but there's the effect of the AO tracking at a specific wavelength and everything moving with respect to that. And so now we see, as we run through time here, 15, 16 degrees, these boxes of the DL-NIRSP. This is the high resolution field of view on DL-NIRSP. And they sort of start to pull in and line up on each other. Especially now we're up to 40 degrees, so there's a lot of overlap now. So this is, but you can see how fast they're moving early on, and then they slow down. So how to line these up and how to is something I think we be a learning experience here as well, but as long as we're aware of what's going on. So this is now similar plot here at a slightly different time where you see, I lost the date down there. So you just see another example of this, the DL-NIRSP effect as things are cycling through. So the other instrument I mentioned was the VISP. And so the VISP has a long, thin slit. Now this has a nice box, and so if these boxes sort of shift with respect to each other, there's still some overlap. With the VISP, what happens when these things shift is now my slits are now covering different parts of the sun at the same time, which part of the goal of having these three wavelengths is you're observing the same parts of the sun at the same time, because otherwise, if I try to interpret the spectrum in this spectral line taken here with a different spectral line taken here, you don't know what you're going to be getting. And so you really want to observe, in many cases, these things at the same time. It's true we can raster the slit and move it across, but still you're going to introduce a time delay often between when you're sampling here. It may be, if this is half an arc second and you're moving the slit, every 10 seconds by a tenth of an arc second. It's too many seconds. But anyway, it could be a minute later before you get to the same spot on the sun with the other slit, and the sun will have evolved by then. So let's see if this one play. Come on. So here you see you're observing in the morning. The slits are shifted. And there's various slits that have various widths with VISP. So now at some point here, they're aligned. Some particular moment, they're all lined up. But then, as I keep observing, they drift off each other again. Yeah?
Is it possible to orient the Goudet rotator so that the direction of this dispersion induced shifting is along the axis of the slit?
Yes, it's like your plant. So I can take my slit and orient it along the parallactic, that direction perpendicular to the horizon, and now my dispersion goes right along the slit. I have some loss here at the ends where I'm measuring in the blue but not in the red at the same time, but the slit is 100 arc seconds long or 80 arc seconds long. That's fine, and these are all lined up, and that's great. Except to do that, if I keep my Goudet rotator and keep it in this orientation, my solar image is going to rotate under my slit. Oop. So now they're all lined up, but now my image is rotating as I'm taking my observations. And this isn't, so bad, I guess, except if you're trying to scan across the sun, and now you're scanning, and it could take an hour to scan a significant region across the sun, and the sun's rotating. And so now you've got a slit that's sort of changing in time, its orientation on the sun. And so that gets just a coordinate transformation issue, but it's complicated because you don't have a regular sampling anymore on the sun. So these are the kind of issues we're going to have to deal with in trying to combine high resolution observations with this atmospheric dispersion effects. And so the exercise, making these images and seeing the effect, there's a little IDL program for doing that. Still working on the Python version. We should be able to do it. By the way, IDL was invented in this building, so. So anyway, so if you go on, we have this program, show field of view dispersion, and all you need is to give it a day of the year. All you need to do is give it a day of the year, because as you saw, that dispersion effect varies with the day of the year, and the minutes after sunrise, and you can sort of go in the range of 0 to 800. As we saw, typical time to start observing is 60 minutes, maybe 45 minutes after sunrise, 60. Anyway, the program has the refraction calculated for a series of different wavelengths. Some key wavelengths, 400, 525, going out to the 1.5 micron line. And so you can sort of provide it a list of 3 different wavelengths, whether that's for the DL-NIRSP or the VISP. Your choice, you can select whether you want to plot the DL-NIRSP field of view in the high or the medium. The wide is actually so big, it's 20 arc seconds, it's outside of the box. Or the VISP, and there's different slits with different widths. You can play with, see how much the overlap is. And then you can tell it to keep the solar image fixed, and it'll rotate the image, the field of view, based on the dispersion. Or you can tell it to line the angle with the horizon, and then you'll see that the image the solar image will rotate. And what it'll display in your X window, just one of these images here, like I was showing you before. So you have, it'll tell you the time and the elevation, which day, and show these the three different boxes corresponding to the three different wavelengths you chose. So this is just a sample calling this, 100. Today is day of the year 154, 71 minutes after sunrise. And what's neat is you can put this in a little for loop, and you can make these movies and see how things change just by having, for minute, that would be minute there as the counter, and you can see, have it gradually increment the minute and see it'll plot the image and show you the change in time. So the software, the show field of view dispersion.pro, and the programs it should depend on should all be on the Google Drive, or following that URL, or go directly to the drive. You can also log on to this server that Jana was mentioning earlier. This is the IP address. Guest, there's a series of guest accounts, guest 1, 2, 3, 4, and so on. This is the password to log in. And then if you change into this directory, you can call IDL and run the program from there and try it out. And yeah, if people need help with that, or if there's any questions. The minimum of the probability of getting good seeing is at noon, right?
And then why you put the telescope in the mountain or in the middle of the lake and sweeper that,
Well, you put it, why, I mean, the mountain is good because you get the good seeing in the morning. Well, right, and so you need also a low sky background, the dark sky. Being away from the jet stream is good, so from a subtropical island. So yeah, there's no perfect sight, but that diurnal variation is most everywhere, but.
I thought that the main reason for Alcalá was the corona site,
Right.
which is not wasn't used in any of the other sites.
Right. I mean, that's right. It's the coronal skies. It was that trade-off between having some good seeing, or the seeing is actually better sometimes in the morning at Haleakala, and it has good coronal skies. It doesn't have some of the stable, moderate seeing at Big Bear, where you get, hours at local noon of good seeing. They looked at even higher mountain lakes, but none of them were as good. Phil?
Is it fair to say that in terms of when you live in the corona, that this you really shouldn't have to worry about this for a variety of practical reasons? Or do you think this might actually be important for those kind of observations?
Off the limb?
Yeah.
And generally, our resolution is going to be lower, right? I mean, here we're talking, looking at the diffraction limited, or below 1/10 of an arc second or something, right? I mean, you have two things. You're going to be looking at the corona at local noon, where the dispersion is naturally, the sun is higher, the dispersion will be lower, and you'll have the DL NIRS per cryo with a large, the resolution is going to be on the scale of arc seconds. So, yeah, I don't think it'll be. And you'll be in the infrared, right? You're probably not going to be looking at the coronal lines at 400 because the sky brightness and the scattering is higher.
But I could imagine trying to look at fine structure and prominences, which are 2 or 3 orders of magnitude brighter than the corona or something.
Right.
But then the question of whether you can use AL on the prominence would come up. The intensity is right enough as well. So I was just
Right.
wondering. I mean, for me, I'm taking away that if I'm going to observe the corona, I'm just going to ignore your talk. But if I really want to look at the
Ignore it
If you want to
anyway.
look at the photosphere
Right.
or the chromosphere, then I better pay attention very carefully to this. Yeah.
Right.
Right. Just want to make sure you
Mhm.
So we sort of hope that he's right and that
Mm.
below a certain
I mean-
resolution we're not going to see anything anyway because the light is not.
That we won't see.
Phil commented that radio transfer would kill some of the
Mhm.
ideas.
Well, it could be. I mean, we already have to deal with this effect in our current observations. Even at a 1/10 of an arcsecond resolution, I mean, we still, this varies. This is an arcsecond shift. This is, tens of pixels that we're seeing our images shifted. We have to deal with this as we look at different wavelengths and try to make connectivity through the atmosphere of magnetic structures. So, even if we're doing, 10 to the 4 polarimetry, or we can't, get to the 20-kilometer resolution, I think there's still some of this that will need to be dealt with.
The corollary of this is, I wonder if we shouldn't ever use a slit instrument on its own.
Mm-hmm.
Right? I mean, because you don't need to. I mean, you could use this with the LNUS or with one of the images, and then
Right.
with a lot you could overlap the continuum, time variations, and things.
Right.
Co-align everything completely.
Right.
So is it fair to say then that you should never use this on its own? Is that what
Well, I mean, you should always have some kind of context, I think.
yeah, but you wouldn't do
right.
it anyway. I mean,
Right.
You're always going to get some context.
Right.
So.
I mean, I think the one thing is we can calculate to pretty high accuracy what the offsets are blindly. We need to verify that at DKIST and with images and so on, but hopefully we'll know, the slits are offset by this much. We'll know how to line them back up to pretty good accuracy.
So I have more of a comment than a question.
Yep.
I was trying to SSH.
Yep.
It doesn't work when I'm on HRO, but it works when I'm on the NSO Wi-Fi.
Mm.
So that might be
Interesting.
similar for other people.
Okay.
If people are,
Has anyone else tried logging in?
it might be because HRO.
No? Did anyone else try logging in from which wireless are you on?
Now,
Weird.
I have already wrote to
Okay.
maybe it's because I'm foreign.
No, it's connecting to this one here. Yeah.
I know that in order for it to connect, I need to be on last Wi-Fi.
I see.
You're connected to better,
I see.
work.
Okay.
It's working fine for me on UCB wireless.
Okay. Any other questions? Yeah. There are no true slit jaw images, right, where you have a slit, which is a mirror with a gap in it, and then you can take an image and you see where you have an image of the slit on the sun, essentially. We don't have that. VISP does not have a slit jaw imager. We have the VBI should be able to take images contemporaneously with the VISP, and so you'll be able to see where it is, and there should be ways to know where the slit is on the VBI image. I mean, there's an alignment between the channels. That doesn't take into account some of the distortions. It doesn't take into account the dispersion, right? Where is my VBI imaging? Which wavelength is my slit imaging? Will introduce shifts there. So yeah. Okay. Has anyone been able to run any of the exercises? Is anything working? No? Yes? You can make your own dancing boxes. Yeah.
Hey, Kevin,
Yeah.
maybe the first keyword, parameter 100 say minutes after sunrise. Wouldn't it be better after start of observation or something, make it the default 0 is 90 minutes? It might be
Which one? The 100? Oh,
In general, I mean, if you start from zero, yes, it's gonna be terrible, but we're never gonna start from zero.
no, yeah, and it breaks, if you go to 0, the calculation is all over the place. It's random. It's tangent of, yeah, it's not good. But, so you have to get at least 5 minutes after sunrise. But I mean, everything's, starting, if we say 1 hour after sunrise is when we can start observing, 1 hour after sunrise we can start observing. So that's a 14-degree elevation. So if you take 60 minutes after sunrise, that's pretty constant during the year, right? If that's so that's a safe number to start with. Okay. So one thing you can look at if you try running it like early in in January with the horizon alignment, you'll really see that image rotation. Or if you run it during the summer, you'll see the image. It'll stay stable for quite a long time, right? It'll stay at 80 degrees, and then it'll flip. The image will spin very rapidly as it goes through the local noon. So that's around, it's in a few weeks, I think, the horizon point. Let's see. Yep.
Is there going to be a field depending on, is the scale of the image going to be changing from one corner of the image to the other? Or is it going to be negligible?
That was the one I was showing where across it was it was 0.998, right? It'll change by a couple parts per thousand. So, yeah, I don't know whether you'd see that in trying to align it. You would need something else with similar resolution. It should be constant. That refraction compression is pretty much constant at all wavelengths, right? So it shouldn't vary between instruments. They should all be compressed the same amount.
Any more questions, or we can you're having fun with the exercise? If not, we can just.
Let's see. So here it is on the 14th of June. Let's see.
Why are there so many?
What?
Why are there so many boxes?
Oh, those were those ones at the top, you mean? That was leftovers from, it plotted the boxes off the image and it left them. Should clean it. It's just doing it going through, so. This is going to take too long. Hold on. Hey, huh? Yeah, I think so. Mm-hmm. Let's see. Welcome back. You just landed, or?
Yes.
Mm-hmm. Okay. So this is on the 14th of June. That's about when the sun goes through the. Yeah. So now it's switched around and it's spinning pretty fast. Actually, the telescope probably cannot track through when it goes through the zenith. There's an exclusion angle, so even if the seeing was good enough to observe at noon, it wouldn't be able to track.
Are there plans to create it's pipelining for the spinning.
This, right, so the data will probably be provided spinning, but there'll be information in the headers to say what the angle is.
Whoever has the deal.
Right, and so then you'll have to, I think, because otherwise you have to, you know,
Okay, yeah.
there's a problem. If you rotate it, then you've interpolated, and it becomes. So it's depending on what you want to do. You may want to have it rotating but not interpolated. So yeah, it should be, and there should be. Right, and there should be, you know, hopefully the goal is to have tools that will say, okay, here you'll read in the header, and then you can derotate it. You can align, take out the dispersion. You know, right? You correct the. Basically, you want to correct the pointing information for each of the boxes, each of the wavelengths. Because normally they'll come out and say they're all pointed at the same point on the sun, but you want to add an offset, a time-dependent offset to the different parts.
I think what you said
Yes? What?
how low is this program about?
5 degrees.
Okay.
Yeah, I mean, the problem is the dispersion was calculated. I mean, it's valid to at above 10 degrees, I would say. The numbers aren't completely crazy until about 5 degrees.